In section 6.2, we're going to be covering 3 different types of volumes of revolution. The first method is called the disk method. After that, we're going to be doing the washer method. And then the third method is volumes by cross-section. So with volumes of revolution, it's really useful for engineering, medical imaging, and we're going to be using a lot of geometry in this. One of the key concepts is this axis of revolution that we're going to be using. So all of our cross sections are going to be rotating about some sort of axis. So to start with, you guys can go to the link on your page, and I'll go ahead and pull this up. The volumes of revolution, for example, we've got our curve right here, f of x, and what we're trying to do, so I'm integrating from a to b, and we're going to be revolving this section, okay, this area under the curve around the x-axis, which is the same equation as y equals 0. So if we increase the number of rectangles, then we have a more exact area under the curve, obviously. And then what we can do is we're going to be revolving around a particular axis. So this is a volume of revolution. So I'm going to go back. And so a lot of times you'll see it's going to be like a smaller section, like from 0 to 6. Okay, so I can increase the amount of rectangles. I can even go a different b, all right? We can go all the way out to the end and we've got 14 rectangles. Okay, so I could spin this around and notice that we're going in a circle. All right, so we are spinning it around and I'm revolving around one axis of revolution. So there's one curve involved and an axis of revolution, and we're revolving in a circle. So everything that we're going to be doing today is going to be involving this volume of revolution that we've got going on. So we're going to start in this image right here. We've got the axis of revolution, and that's what we're going to be taking this f of x, and we're going to be revolving around. This region R, that's called the radius. Okay, so we can think the same thing that we've been doing for areas of areas under the curve, all right, where we've got two curves right here. So we've got their top curve, which is f of x, and then mine is our bottom curve, which is my axis of revolution. In this case, we've got C right here, so we could call this y equals C. And we are revolving in a circle, and it chose to be this image. So as I mentioned, we are revolving in a circle. So the area that we're going to be integrating is pi r squared because we are going in a circle. If you notice here, we've got pi times, and then this was our top curve, and then we've got minus our bottom curve that they inserted into the radius right here. So our radius changes from our top curve to our bottom curve, and that's essentially what we're integrating. So to find the volume of a solid, we're going to be integrating from a to b. So we've got pi, that's a number, we move it to the outside, and then you've got your radius right here, top minus bottom, and then squared dx. So again, pi r squared dx that we're integrating from a to b. And similar formulas can be derived if our axis of revolution is vertical. So if we've got a vertical axis of revolution, a vertical axis of revolution, we would be doing our radius for y, that would be our right minus your left. And an axis of revolution, that's going to be a stationary, okay? So it's going to be a singular line. And if our radius is in terms of x, because we have a horizontal axis of revolution, that's going to be top minus bottom. So you can see in these two pictures right here, so A and B are along the x-axis. So in both of these, we're going to be revolving in terms of x. Right here, my axis of revolution, it looks like it's something like y equals 1. So I could say, okay, our radius would be f of x, and then you've got minus 1 for the axis that you're revolving around. So my axis of revolution right there is y equals 1. So for the volume, we could say the volume is going to be pi integral a to b, and then you've got your top curve minus your bottom curve squared for r squared, and then you've got dx. We've got pi r squared dx. Now on this one, it looks like my axis of revolution is -1. And if you think about top minus bottom, notice that, so for my radius, notice that the top curve is the axis of revolution. So we've got -1 on top. So we're going to do top, and the minus f of x is below that. So top minus bottom. So for this one, we've got pi integral a to b, and we've got our top curve minus your bottom curve, top minus bottom, the radius squared, dx. So it's pi r squared. We are revolving in a circle. So we are going around our axis of revolution, right? Again, around our axis of revolution right there to get our volume of revolution. So in these problems, in this page and the next page, the next couple of pages, we're going to be finding the volume of revolution, and it's always going to tell you what you're revolving around. So we've got different things that we're revolving around. In question number 1, we're revolving around the x-axis, and same thing in question number 2, again, revolving around the x-axis, and then we'll get into the next page where we're revolving around a different axis. So question number 1, we're going to have to graph this. So it says, find the volume of revolution. So we are doing a volume of the solid generated by revolving. So we are going in a circle. And then we've got this curve right here, y equals x squared. And then we've got the other curve, which is y equals 0. And it says about the x-axis. Well, we know graphically the x-axis and y equals 0, that's the same thing. So let's go ahead and actually draw this graph. So to graph this, we can go ahead and factor. So we've got 0 equals x times 1 minus x. So we've got zeros at 0 and then at 1. So I'll go ahead and go out a little bit more and plot that right there. And then, so this line is going to be, that would be y equals x minus x squared. And then our other line is this y equals 0, which happens to be the y-axis. So I'm also going to write down that that's my axis of revolution because that's what we're revolving around. So our goal is to take this region right here in between 0 and x minus x squared, and we are revolving it all around the x-axis. All right, so our radius, we can go and do top minus bottom for our radius. So we've got x minus x squared and then minus 0. So that's our radius. So the setup for this volume problem would be pi integral, and again, it's where the two lines intersect. So 0 set equal to x minus x squared. We already have our zeros, 0 and 1, and then we've got x minus x squared, and then you've got minus 0, pi r squared, and then we've got dx. So again, don't forget about the fact that this is pi r, this whole thing is r, and then we've got squared for a circle. After this, you're going to go ahead and actually integrate. So we've got pi, and then we've got our integral from 0 to 1. Keep in mind algebra. So when you square this, it is not distribution. You have to write it twice and then multiply it out. So you'll have x squared minus 2x cubed plus x to the 4th dx. And then you can go ahead and add and divide and then insert your 1 and your 0. Go ahead and pause the screen, and when you're finished, go ahead and unpause it. So as you go along, just make sure that you are putting the pi in the very front, and then 1 times 1 over 30 will get you your final answer of pi over 30. Question number 2, we're going to do the same thing. We're going to start by graphing this, and we're going to revolve this around the x-axis. So we're going to go ahead and set up your graph. You're going to factor it and graph. So when you factor this, you should get zeros at 0 and then -3. Because the leading coefficient, even though it's not in the correct order, is negative, it's going to be concave down. So using all of your math knowledge from ever, you have to know how to graph these by hand. And then we're going to be revolving around our axis of revolution. And this right here, this vertical line there, is for my radius. In this case, we've got -3x minus x squared, and then minus the number for the axis of revolution, which happens to be 0, so that our volume is pi integral. All right, where our two lines intersect are our bounds of integration. So we've got from -3 to 0, And then we've got negative 3x minus x squared minus 0, which is not needed, squared dx. So again, just like the previous problem, when you multiply this, you have to split it up. You're going to write it twice and distribute. So you're going to have 9x squared plus 6x cubed plus x to the fourth dx. And then when you go ahead and work on all the way through this, you'll end up with pi times 81 over 10. Again, work this out and get to the 81 tenths with a pi in front, which means that this is going to be 81 pi over 10 as our final answer. In question number 3, we're just doing something a little bit different. We are revolving around the y-axis this time. So we need to know how to graph these. So notice that these are both in terms of, well, this is in terms of x, so we're going to have to get this in terms of y. So this would be the same thing as saying 2y equals x. We just multiply the 2 over. And then you've got x equals 0, y equals 2 about the y-axis. So again, knowing our knowledge about the y-axis is when x equals 0. That means the same thing. So let's go ahead and graph this. So we can graph it in terms of x. We can use the fact that y equals 1/2 x. So we've got an intersection at 0. All right, our y-intercept is 0. And then we go up 1, right 2, up 1, right 2 for our slope. So this right here, that right here is the line of y equals 1/2 x, or we can say in our case, x equals 2y. Because we're going to be revolving around the y-axis, which is right here, the y-axis, and that is going to be the line x equals 0. That happens to be my axis of revolution. And then the other line that we have to draw is that y equals 2. So I'm going to go up to 2, and I'm just going to draw a line going through that. So you've got the line y equals 2. So this right here is our graph, and we are going to take this region bounded by all of this, and we are revolving it around the y-axis. So for our radius, you're going to do the right minus your left. So I'm going to go ahead and touch the y-axis. I go ahead and make, that's a perpendicular line with, and that's what we're revolving around. We're revolving around the y-axis. So our top curve is 2y, and then the bottom curve is 0. So that's our radius. So for our volume, you've got pi integral, and then we've got 2y minus 0 quantity squared dy. Well, our bounds also need to be in terms of y. So our bounds being in terms of y, this is going to be at y equals 0 is right there. And this line is y equals 2, and I've got an intersection at 2. So right here, we intersect at, it looks like 4, 2, which is perfect because we need that 2. So we're going from 0 to 2. And then we can go ahead and anti-derive this and find our answers by inserting the 0 to 2. Please make sure that you are using your exponent rules. So 2y, the entire quantity squared, gets you 4y squared. Add and divide, 4/3 y cubed with the pi in front. Don't forget to bring down the pi. Insert the 2, insert the 0. So you've got 2 cubed, 8 times 4, 32. Pi goes on top, divided by 3. The last one that we're actually going to do is this number 6. So we're going to go ahead and start by graphing this. So if when we graph this, this is going to be a concave down parabola starting at 3, and then you don't really care where you hit the x-axis because one of my graphs is y equals 3 minus x squared, but the other one is y equals -1, and we're revolving around this y equals -1. So at y equals -1, that's my axis of revolution. So we've got y equals -1. That makes our radius 3 minus x squared, and then minus the -1. So we can insert that into our volume formula, except for the last thing that we need are the bounds. you are still going to set these two equations equal to each other to solve and find the bound. Don't forget when you